Hello learners, welcome to this course on Embedded System Design using PIC16F877 microcontroller. In this tutorial, I will be discussing about on how to transfer the temperature sensor data to PC using PIC16F877 microcontrollers UART. So the temperature sensor which we will be using is LM35. So first let us start with the fundamentals of your UART. So UART is a universal asynchronous receiver transmitter. So it is used for transferring the data in a serial fashion. So bit by bit transmission can be done. And it works in asynchronous mode of transmission, which means it does not require a clock source to transmit the data. So here if we see the packet format for a UART protocol, so it starts with a start bit. So the start bit is represented by a logic high to 0. Then comes your LSB bit. Then subsequently the data bits are being transmitted. Then finally your MSB bit. So after your MSB bit, we can have a parity bit. So the parity bit can be an odd parity or even parity depending upon the number of ones on your data. So if I have odd number of ones, then it is called as a odd parity. If I have even number of ones, it is called as an even parity. So even parity is represented by 0, odd parity is represented by 1. Then after your parity bit, we will be having a stop bit, which is nothing but low to high transition. So here the data bits can vary from 5 bits to 9 bits. It is a user configurable one. So it can be varied from 5 bits to 9 bits. So here we start with the start bit, then comes the LSB data, finally comes your MSB data, then your optional parity bit, and then finally your stop bit. So this is the packet format for your UART protocol. So here the logic 1 and logic 0 is represented differently for a microcontroller and for a PC. For example, in case of a microcontroller, it works with the TTL logic. So logic 0 is considered as 0 volt. Logic 1 is considered as 5 volt in case of a microcontroller. Whereas in case of a PC, logic 0 is treated as plus 12 volt and logic 1 is treated as minus 12 volt. So if you see the logic 1 and logic 0, voltage levels differ from a microcontroller and to the PC. So there is a requirement of voltage doubling and also there is a requirement of voltage inverting. So both are required. So in order to transfer a data from your microcontroller to PC or from PC to a microcontroller, we need to do these two things. One is voltage doubling and also voltage inversion. So that is taken care by your MAX232 IC. So MAX232, it does both voltage doubling and voltage inversion. And it also converts your TTL logic to RS232 level logic, and from RS232 it can be converted to TTL logic. So for example, if I consider, if we want to transmit a data M, so M ASCII value is given by 1001 101. So if I count the number of ones here, we have 4 ones, so it is about even parity. Then how the signal transmission will be? First, there will be a high to low transition which indicates the start bit. Then comes your LSB part. So LSB is 1. Then 0, 1, 1, 0, 0, 1. So after your MSB, we will have a parity bit. So the parity bit, since it is a even parity, it is represented by 0. And then we have a stop bit which is low to high transition. So this is how the signal gets transmitted using a UART protocol. Now let us talk about LM35, which is a temperature sensor. So the temperature sensor is shown here. It has 3 leads, 1, 2 and 3, where the pin number 1 is a supply voltage. We can provide a supply voltage of about 4 volt to 20 volt. And pin number 3 is your ground line, and the pin number 2 will be the output line. This output line voltage changes with respect to the temperature. So for every degree centigrade, a 10 millivolt variation can be seen. So for example, if the room temperature is 30 degrees, From pin number 2, we will be able to get 300 millivolt as an output. So for each degree centigrade, 10 millivolt variation can be visualized on this pin number 2. So this LM35, it can measure the temperature from minus 55 degree centigrade to 150 degree centigrade range. And it has an accuracy of about 0.5 degrees is possible. And it operates at 4 volt to 20 volt. So in this tutorial, what we will be doing is, we will be connecting a LM35 temperature sensor to PIC16F877 microcontroller, read the temperature sensor value, put that value onto an LCD. So LCD which we are going to use is 16 cross 2 LCD, and then send the data to your computer using MAX232 driver through this transmitter and receiver lines. So the transmitter and receiver lines for your UART protocol is available in RC6 and RC7. So RC6 is multiplexed or dual functionality is your transmitter line of your UART. RC7 dual functionality is receiver line of your UART. And from the MAX232 driver, it doubles the voltage and also it inverts the voltage, and the signal goes to your DB9 connector. This DB9 connector gets connected to your computer. In case of a DB9 connector, usually a male connector will be available in the computer. So we need to take a female connector from your microcontroller, and this female connector can be connected to the male connector of your computer. So if you see the pin details, so this is the male connector DB9 connector. So if you see, the pin number 1 starts on the left side. It goes to 5 and then again 6 on the left side, at the bottom to 9. Whereas in case of a female connector, it will be just opposite. So from on the right side, the pin number 1 starts, 1 to 5 it goes towards left, same way 6 to 9 it goes towards left. So if you see, the 3 important lines which we will be using is the transmitter line, receiver line and the ground line. So the transmitter line is pin number 3, receiver line is pin number 2 and ground line will be 5. All the pins are your handshake signals, like DTR is a data terminal ready. CD stands for carrier detect, RI stands for receiver indicator, CTS stands for clear to send, RTS stands for request to send, DSR is for data set ready. So we will be mostly using these 3 lines, pin number 2, pin number 3 and pin number 5. So pin number 2 will be your receiver line, pin number 3 will be your transmitter line and pin number 5 will be ground in case of a male connector. In case of a female connector, pin number 2 will be the transmitter line, pin number 3 will be the receiver line and pin number 5 will be the ground line. So it will be just reversing. This pin number 2 and pin number 3 will be changed. Here in male, it is pin number 2 is receiver, whereas in female, pin number 2 is your transmitter. Usually on the PC side, you will be having a male connector. So from the microcontroller, we have to use a female connector. So this is what we are going to do. We are going to measure the temperature using the LM35, put that value onto the LCD and the same value will be sent to your computer also. Now let us go and build the circuit using Proteus 8 Professional and build the embedded C program using Micro C Pro for PIC. Then after compiling your program, the hexadecimal file will be loaded onto the microcontroller in your Proteus 8 environment. Then we will check the result. Now let us go and see the circuit diagram for your transferring of data from microcontroller to PC. So here if I see, we take a PIC16F877 microcontroller, then it is connected with a oscillator of 20 MHz. Then we have a reset circuit connected to your microcontroller and then LM35 temperature sensor. It gets connected to your RA0 AN0 pin. So in channel 0, we are going to connect the LM35 temperature sensor output. Then in the port D, I have connected the LCD. So in a 4-bit mode, So D4, RD4 to RD7 is connected to D4 to D7 of your LCD. Then enable line is connected to RD3. RS line is connected to RD2. So RW bar line, D0 to D3, VEE and VSS all are connected to ground. Then VDD is connected to a supply voltage. So D4, RD4 to RD7 is connected to D4 to D7 of your LCD. D0 to D3 is grounded. We are going to use the LCD in a 4-bit mode. So we try to ground the D0 to D3. Then 3 control lines. RS connects to RD2. Enable connects to RD3 and RW bar is connected to ground, which means we are going to do write operation. Then we have 3 power supply lines, VSS connected to ground, VDD connected to supply and the contrast adjustment, which is VEE, is connected to ground, which means we are going to have a high contrast. Then we take the transmitter and receiver line from RC6 and RC7. It gets connected to your MAX232 IC. So this MAX232 IC, it does 2 things. One is voltage doubling and also voltage inversion. So this conversion process is done with the help of your capacitors connected to pin number 1, 3, 4, 5, 6 and 2. So we have the capacitors connected to this MAX232, thereby the voltage doubling and voltage inversion will take place. And the output of your MAX232 will be connected to a hyper terminal. So this hyper terminal is mimicking the computer. Now we will try to measure this temperature sensor data using a microcontroller, send the data to your hyper terminal and also to the LCD. Now let us go and visualize the programming part. So we start with our LCD connections. So LCD RS is connected to D2, enable is connected to D3 and LCD D4 is connected to RD4, D5 is connected to RD5, D6 is connected to RD6, D7 is connected to RD7. Then the corresponding data direction registers are configured. Then we declare few variables like temperature hex, temperature volt and 3 character variables CH1, CH2, CH3. In a main program, first we disable all the interrupts. So intcon is a interrupt control register which is used for configuring the interrupts. So we are not going to use the interrupts, so it is set with the value of 0. Then in TRISC, I am going to set the value as 0x80. So 0x80 means this is 80. So here I am going to use these 2 lines. So RC7. So this RC7 is a receiver line. RC6 is your transmitter line. So transmitter line is configured as an output. Receiver line is configured as an input. So that is why we put 1 and 0. So if I put 1 to a bit on a data direction register, the corresponding pin will be configured as input. If I set it to 0, then the corresponding pin will be configured as an output. So here RC7, we are setting it as input. RC6, we are setting it as output. Then ADCON1 is a to D control register 1. Here I am setting it with 80. So this is used for making the port A and port E lines to be analog values. It will support analog values. So that is why we use this ADCON1. So port A and port E of PIC microcontroller is connected to A to D converter. So I want to make this port A and port E to be analog pins. So for that we set a value of 0x80. Then TRISC A equal to 0xFF, which means all the port A pins are configured as an input pin. If I set 1 to each bit, then it will be configured as input pin. So we put FF, so meaning all the port A pins are configured as input pins. Then since we are going to connect a LCD to port D, I am going to set it as an output port. So TRISC D equal to 0x00, which is your output port. So after the normal port configuration, we go with ADC configuration. So here I am going to use the library function ADC_int, which means we are going to configure the ADC, and the ADC's conversion clock will be depending upon the internal RC oscillator. So internal RC oscillator will be used for the conversion purpose. Then I am going to initialize the LCD, then send some commands like LCD_clear to clear the command register and data register. Then cursor is off. Then I put a text in the first row, first position. I am going to display temperature. In the second row, first position, I am going to display measurement. So in the first row, we will get temperature. In the second row, we will get measurement. So in order to visualize this output on the LCD, I am going to retain this output for some 2 seconds. Then I am going to clear the content of the LCD. Then we need to initialize the UART also. So UART we are going to set with a baud rate of 9600. So 9600 bits per second is the speed at which the data will be transmitted. So you are going to use a UART with 9600 bps. So we give some time for the UART to get initialized. Then I am going to test that UART connection by sending temperature measurement to the computer. So from microcontroller, the temperature measurement will be sent to the PC. Then we put a new line and a carriage return key. After this, we go to a while loop. So in a while loop, I am going to measure the sensor value. So the LM35 is connected to channel 0. So I try to read that value. Then do the conversion process. So the converted result will be available in the temp_x. So the converted value will be a 10-bit value. So it will take a value between 0 to 1023. So 10-bit in the sense 2 power 10 is nothing but 1024. So my value will vary from 0 to 1023. So this is a hexadecimal value. I want to convert this hexadecimal value into a voltage. So in order to do that, what we do is we take the hexadecimal value, multiply it with 4.88, where this 4.88 is nothing but the resolution of your ADC. If my reference voltage is 5 volt, then the resolution is computed by V reference divided by 2 power n minus 1. So V reference, if I take it as 5 volt, which is 5000 millivolt, so 5000 millivolt divided by 2 power 10 minus 1. So which is nothing but 5000 millivolt divided by 1024 minus 1, which is 1023. So we take, what we ultimately do is we compute 5000 divided by 1023. So which is equivalent to 4.88 millivolt. So this is the resolution of your ADC. So this is the smallest voltage change which can be properly represented in a binary bit pattern. So we multiply this resolution into the hexadecimal value, we get the temperature in terms of voltage. Now I want to put this data onto a LCD and also to a UART. So for that, what I do, I need to split the data separately. For example, let us assume the room temperature is 32.3 degrees centigrade. Let us assume the room temperature is 32.3 degrees centigrade. So the measured voltage will be 323 volt, 323 millivolt, because for each degree centigrade, LM35 will produce 10 millivolt variation. So 32.3 degrees centigrade is equivalent to 32.3 degrees centigrade is equivalent to 323 millivolt, right? Because each degree is represented by 10 millivolt variation. So we multiply 32.3 into 10, which is nothing but 323 millivolt. So now what I am going to do, I am going to separate each digit. So I am going to separate this 3 and send it to LCD. Then I am going to separate this 2 and send it to LCD. Next I am going to separate 3 and send it to LCD. So like that we are going to split the data into different characters and send the corresponding value to LCD and your UART. So in order to do that, what I do is I take this temperature volt. So this is nothing but 323. So 323 divided by 100, which means I get a quotient of 3. So 3 will be stored in CH1. So CH1 will have 3. Next, what we do, I have taken this 3. Next, I want to take this 2 out. In order to take this 2 out, what we do, again we take 323. So temp underscore volt is 323 divided by 10. So divided by 10 in the sense 323 divided by 10, which is equal to quotient value is 32. Right, so 32.3. So we take the quotient value alone, so it is 32. So after 32, what we do, we take the mod of 10. So mod means we will get the remainder value. So 32 mod 10, which will give the remainder value, which is 2. We will get the remainder 2. So the second digit is obtained. So 2 is obtained in the CH2. So CH2 is having 2. Next, what we do, we take again temperature volt. Now we will compute the mod of 10. So 323 mod of 10. So mod means remainder value, which means I will get a value of 3. 32 is your quotient and 3 is your remainder. So I get 3. So CH3 will be equal to 3. So you can see we have splitted the character. In CH1 I have 3, CH2 I have 2, and CH3 again I have 3. So 3, 2, 3. Now I can convert this data into a ASCII value and send it to your LCD and the UART. So that is what we are going to do now. So first I put in 1,1 temperature. In 2,1 I put temperature equal to. In the first row we put temperature. Second row we try to put temp equal to. Then I am going to convert this CH1. CH1 is nothing but 3. So this 3 is a hexadecimal value. I want to convert it into a ASCII value. So for converting it into a ASCII value, if you see the ASCII chart, if I want 0, means my decimal value is 48 here. Right? So I have to add 48 to this 0. Same way for 1, my decimal value is 49, which means 1 plus 48 I have to do. 2 means 2 plus 48. 3 means 3 plus 48, which is nothing but 51. 4 is 4 plus 48, which is 52. So like that I have to add 48 with each hexadecimal value so that I get the corresponding ASCII value. So what I do, CH1 plus 48, put it on to a particular position on the LCD, then CH2 plus 48. So here I display 3. Next one is 2. Next I am going to put decimal point, a decimal point. After this again I put 3, which means I get 32.3. Then I give a space. So this is space. Then I specify C. So our LCD will display 32.3 centigrade. So the same data is also sent to your UART. So here you see in the UART write text, I send the temperature, then CH1 plus 48, CH2 plus 48, then decimal point, then CH3 plus 48, then space C, then your new line and carriage return. So the same data is sent to your LCD as well as your UART. In order to retain this data, we use a delay function of 2 seconds. Then afterwards, I am going to clear the LCD. Again, since it is in a while loop, again the sensor data will be read, converted into a hexadecimal value, convert this value into a voltage, then split the data, put it onto LCD and UART. So this process continues again and again. So thereby the temperature sensor data will go to your PC. So once the programming is done, we can build the circuit. After building, we can go to your Proteus environment, load the hexadecimal value, right clicking on the microcontroller, edit properties, select the hexadecimal file. So this is the hexadecimal file, UART_ADC, which is a hexadecimal file. Select this file. Select the oscillator frequency also. So here I am going to set it as 20 MHz, and in the microcompiler also you can see the IC is PIC16F877 and the oscillator frequency is 20 MHz. So the same frequency is used here too. Press OK. So now we have loaded the hexadecimal file onto your microcontroller. Now let us run and visualize the output. So here you can see temperature measurement. Here you can see in UART temperature measurement, the temperature is shown. In LCD also it is shown. So when I start increasing the temperature value, you can see the change 26.3 here. In LCD also there is a variation 27. So like that I can increase or decrease the values. So thereby we can see the data in both LCD as well as in a UART communication. So in this tutorial I have talked about how to interface a LM35 with PIC16F877 microcontroller, how to measure this data and send it to a computer, and also visualize the data in an LCD. Thanks for watching. Please subscribe for more technical learning. Thank you.